Okay, so this is going to be the first lecture from Chapter 16 on traveling waves. The two chapters 16 and 17 are both on waves, and these will be the last new material that we are going to cover in Physics 1, in Physics 313. So here we go, we're almost to the end. Okay, so as the title suggests, we're doing traveling waves in this chapter. So what is a wave? Well, we're going to decide, we're going to find out that it's a disturbance traveling through a medium, right? So the medium tells you what exactly is waving. We can split up or classify different kinds of waves in different ways. So for example, one way we can classify waves is the direction of wavage as compared to the direction of travel of the wave. In a transverse wave, as you can see here in this picture, the wavage, that is the disturbance, is perpendicular, in this case up and down, whereas the direction of travel is sideways. So the direction of disturbance is up and down, and the direction of travel is sideways, and those are perpendicular to each other, so we call that a transverse wave. The other possibility is that the direction of travel is the same as the direction of wavage. And you can see that here the squishage and expandage of this spring are in the same direction as the direction of travel of the wave. So we call that longitudinal. We also are going to be talking about different kinds of wave properties. We've already seen some of these when we were talking about harmonic oscillator, and we're going to see again that these same kinds of properties we can also attach to traveling waves. So wave speed is the v, that's the speed with which it travels through the medium. Wave length is the distance between two neighboring crests or troughs or any two points that correspond, just as we had for the harmonic oscillator. And so that should sound familiar. Frequency is the number of oscillations per second. Again, this is exactly the same as we had for harmonic oscillator. And amplitude is maximum displacement. Again, that's exactly the same as what we had for harmonic oscillator. Okay, we're also going to talk about particular kinds of waves. We're going to talk about waves on a string. We're also going to talk about sound and light, and those are also kinds of waves. The sound waves are longitudinal waves, and light waves are transverse waves. So we have very important examples of both kinds of waves. Waves where the direction of travel is in the same direction as the disturbance, and waves where the direction of travel is perpendicular. And we're also going to talk about how waves carry energy and momentum, as a matter of fact. We're also finally going to talk about the Doppler effect, because you can't have an intro physics course that includes waves without talking about Doppler effect and how the police are able to tell that you're speeding. And that's kind of silly. All right, so we're going to go through the reading questions because you've already done them in your homework, and get right into the wave model. Okay, so what is a wave model? Well, the model of a wave is that we've got a disturbance. Okay, it's a disturbance that travels in both time and space. Okay, so it's going to be the amount of amplitude of difference from equilibrium is going to be a function of both x and possibly y and z, both position x and time t. The medium is the substance through or along which the wave travels. That is, it's the thing that's actually waving. So for example, for a water wave, the thing that's actually waving is the water. So the water here is the medium. Okay, so here is a better picture, a bigger picture of a transverse wave, and here's the definition. The wave, a transverse wave is a wave in which the displacement is perpendicular to the direction in which the wave travels. So for example, if you took a stretched string and you moved the string up and down like this, then that could create a bump which would then move to the side. And the bump is in this direction, and the motion to the side is in this direction. So those two directions are perpendicular. So this is an example of a transverse wave. Okay. A longitudinal wave, on the other hand, is one in which the direction of travel is the same or parallel to the direction of the disturbance, the amplitude that it's going away from equilibrium. So, for example, if I took this slinky here and I pushed and pulled it back and forth like this, then the disturbance in the slinky would move down this direction, and you can see that the coils are close together or farther apart, or closer together or farther apart, and so the disturbance is in this direction, but the actual motion of the wave, that is, as it travels down the slinky, is also in this direction. So we call that a longitudinal wave. Okay, now the speed of a wave is a function of the medium. So for example, if you're talking about a wave on a string, on a stretched string, like what we had in a couple slides ago, the speed of that wave is the square root of the tension divided by the mass per unit length, or the linear density. That's what we're using here as mu. So that's the mass per unit length. So that's the speed of the wave on the string. Notice that it's only a function of the medium. You can change the speed of the wave in the string by changing the tension, or by using a whole different piece of string that has a different mass density, but the speed of the wave doesn't change if I just change the amplitude, for example, of the disturbance. Okay, so the speed of a wave is a function of the medium, and in the case of a stretched string, it's just given by the square root of the tension divided by the mass density. Okay, so here we have a quick check question. We've got two wave pulses traveling along the same stretched string. It's the same string, one after the other. One of them has a smaller amplitude and one of them has a bigger amplitude. And one of them has a, well, okay, I guess that's it. One of them has a smaller amplitude and one of them has a bigger amplitude. And so the question is, how do the wave speeds compare? And we just got through saying that the speed of the wave is not a function of the amplitude. So the correct answer here would be C. All right, so suppose we wanted the wave pulse to travel twice as fast. So how could we make that happen? Well, if we increase the string tension by a factor of 4, then when I square rooted it, we'd get an overall factor of 2. So that would be one way of doing it. Okay, now let's talk about graphs. This is a little bit tricky, so we're going to spend some significant amount of time on this. What is it we're talking about here? Well, notice that, as always, whenever we draw a graph, we want to label our axes. In this particular case, we're calling the disturbance y. Why are we calling it y? Because it's a bump up or down. So we're calling this direction x, so we're calling this direction y. So this is delta y, that is the disturbance in the y direction, as a function of x. And this is a snapshot graph, because why? Because it's like a photograph taken at a particular point in time. So all of these points here, they're all at different x's, but they're all at the same time t. So it's literally a picture of the wave at that instant. Okay, so here we have successive snapshot graphs of the same wave, but at different times. Excuse me, this top graph is labeled T1, then we have T2, which is a later time, and then we have T3, which is a still later time. And we can see that the wave goes from here to here to here. So it's moving in the positive x direction. So as the slide here says, they're like successive frames from a movie. And we notice that the wave pulse moves forward a distance delta x equals v delta t during the time interval delta t. In other words, the wave speed v tells you how far any point on a snapshot moves in an amount of time delta t. Okay, so there it is right there. All right, a history graph, on the other hand, tells you what the disturbance looks like as a function of time for a given value of x. So we're calling it a history graph because it gives you lots of t's but only one x. So this is the history of position x1. Notice that it's backwards. Why is that? Because this is at earlier times and this is at later times. So if the wave is moving in the positive direction of x, then it will have, so x will have, these are the earlier points where x was, and this is the later points of the later points in time at position x1. Okay, so that point is made a little bit clearer here on this two-dimensional, or actually three-dimensional graph. Here's t going from 0 to larger positive times. Here's x going from 0 to larger x values. And you can see that if you look at the snapshots like this, then this is the sequence of snapshot graphs that we saw a couple slides ago. So that gives you snapshot graph, snapshot graph, snapshot graph. Putting all those together at any one value of x gives you a history graph. So for example, if you're interested in this particular, this particular value of x, say, then you're going to see these earlier points sooner. So at earlier points in time, at this one particular value of x, here's where you're going to see higher and then lower and then lower and then 0. Okay? All right, so here's an example, and we're going to go through this in a little bit of detail so that you can actually see what's going on. All right, so this is a snapshot graph at t equals to 0. Okay, and we want to get a history graph. Well, the way we're going to do that is we're going to say, okay, this is a snapshot graph at t equals to 0. If I'm interested in a history graph for the position of x equals to 8, then it's going to be 0 until something gets up to here. So that's not going to happen until the leading edge gets here in this amount of space. Now, if it's going at 2 meters per second, then 1 second later, from t equals 0 seconds, the leading edge will be here. And then 1 second after that, the leading edge will be here. So it's only 2 seconds later that we're going to actually see something. And what are we going to see? Well, we're going to see that it's going to start to go down. Okay? So that's what we're going to see first. But we're going to see 0 as a function of time at x equals to 8 meters. We're going to see nothing until t equals 2 seconds. And then we'll see something going down. So at 2 seconds, we'll see something going down, and then it will go up, and then it will go down again. So here we are right here. Here's the snapshot graph, and here's the history graph at x equals to 8 meters. Notice that first it goes down. It's 0 up until 2 seconds. That's because the leading edge didn't get here until 2 seconds later. But then it goes down. It goes down because why? Because that's what is first seen at x equals to 8 meters. So it goes down here, and then it goes up, and then it goes down again. So notice it's sort of backwards from the direction of what the snapshot graphs look like. But you can see exactly why that's so. Okay, so here's a snapshot graph at t equals 1 second of the wave pulse traveling to the right at 1 meter per second. We want to know what shows the wave pulse at 2 seconds before, okay, at t equals minus 1 second, right? So here's what it looked like at t equals 1 second. 1 second ago, this thing was 1 meter earlier. So the slice downwards would start here and go right through there, right? And 1 second earlier, the slice downwards would start one over here, right? So it would start at -2 and then go downwards to here. So I think the correct answer is here, A. And there it is. Okay, let's look at this one. We want to know the history. Oh my goodness. All right. This is completely wrong. Why is this completely wrong? Because none of these graphs shows a history graph. What's a history graph? A history graph is a graph that's a function of time, and all these alternatives are functions of distance. So these are all wrong. Let's see what it says the right answer is. Right? It says this, right? Now, this would be correct, okay, if this were labeled correctly, but it's not. So, all right. How about a longitudinal wave? Well, a longitudinal wave, the displacement is along the same direction as the direction of travel of the wave. And you can see that here's the direction of the travel of the wave. It's along the x-axis. But now the displacement is written as delta x because that's in the same direction as the direction of travel. So this is delta x as a function of x. And the what's going on here is that the points get spread out or scrunched together, or spread out or scrunched together. And that's the displacement in the same direction as x. So this is a good picture to keep in mind when you're thinking about sound waves, because that's exactly what sound is. It's a longitudinal wave in which the air molecules, if you're talking about sound in air, get bunched together and then spread apart and bunched together and spread apart. And that's how the wave then travels through the air, by bunching and spreading and bunching and spreading, and then they impinge on your eardrum and you hear whatever the heck it is. Okay, so here's here's a wave at a sporting stadium, which I guess we're not going to do anymore until COVID goes away, but whatever. Notice that he's going to just use d as a displacement. Okay, so this could be displacement in the same direction, longitudinal, or displacement in the transverse direction, that would be transverse, and we're just going to call it d as a function of both position and time. Okay, so here again we have the three-dimensional graph. Here we have the x direction, and here we have the t direction. So the wave at t equals to 0 looks like this. At a little bit later time looks like this. At a little bit later time looks like this, and so on. Notice that the wave travel is going this way. The wave crests move with a steady speed towards larger values of x at later times t, right? If this is a harmonic wave, then these these oscillations here look like a sine or a cosine. Okay, so here we have a sine function. Here's the amplitude as a function of time, and this is therefore a history graph because it's d as a function of t. We could also have a snapshot graph, which would be d as a function of x. If it's a sinusoidal wave, it's going to look like a sine in either x or t. Okay? In other words, it's a sine function of both x and t. And so here it is as a function of x, and you can see that the oscillations again look completely sinusoidal. Notice that the wave is going in the positive x direction, and we can label the distance between any two crests as the wave length, or the distance between any two troughs as the wave length. And we can also label the distance between the 0 amplitude and the largest amplitude as a, the amplitude of the wave. Notice here, if the d is plotted as a function of t, the distance between any two crests is the period, because that's the time over which the wave has to travel in order to repeat itself. This is a period. This is a wavelength. Okay, so here's another check question. We've got a wave on a string traveling to the right, and at this instant, what's the motion of the piece of string marked with the dot? Well, you can see that if the wave is traveling to the right, then the very next instant, this wave will be a little bit over to here, which means that this will be a little bit down to here. See? Here we've got sinusoidal waves with the crest moving to the right, and you can see that the little arrow here, the black arrow, points to where this particular crest is as a function of time. So you can see that it's going to a bigger x as time goes on. And that's correct because the wave is moving to the right. All right, so how do we get the distance span between one cycle of the motion? Well, that's the wavelength. Similarly, the time interval spanned over a period t that would be plotted on the history graph. But the speed, which is a constant, remember it's a function of the medium, is the distance divided by the time. So the distance that the wave travels in that amount of time, capital T, is lambda over t. All right, so that's the v, that's the speed of the wave, the distance that it goes in one cycle, and this is the time that it goes in one cycle. So the speed is lambda over t. And notice that it has the right units, because speed has to be in meters per second, and lambda is in meters, and period is in seconds. You can also put this in terms of frequency, since 1 over the period is the frequency. So speed is also equal to lambda times the frequency. So again, notice that the units are correct here, and either this equation or this equation is on your formula sheet. All right, so they want to know here the period of the wave. Now notice you can't read it right off this graph, because why? Because the distance between any two crests here is going to be in meters, as you can see from the label on this graph, on this axis. But you are given the speed of the wave. The speed of the wave is 1 meter per second. You can read off from the graph the lambda. The lambda is clearly 2 meters, and so if we divide the speed 1 meter per second by the lambda 2 meters, you have to get 1 per second. So that's the frequency, all right? And remember, the period is 1 over the frequency, so it's 1 second. Oh, sorry. Did I say 2? I guess I did say 2. Sorry about that. The wavelength here is in fact 2 meters. So sorry about that. So, woo! Where's my brain today? Okay, so let's go through the mathematics of the sinusoidal waves. Here's the angular frequency, just like with the harmonic oscillator. The angular frequency is 2 pi times the frequency, or 2 pi divided by the period. The wave number, this is something new. The wave number we're defining as 1 over the wavelength times 2 pi. All right. In terms of the omega and the wave number, we can write the full mathematical equation for the displacement as a sinusoidal function of both the wavelength and the period. And of course, we can also tack in an arbitrary constant here for the phase offset. Okay. Notice that we can also write down the speed in terms of the omega and the k, because the speed v was lambda times f, okay? But lambda is 1 over k times 2 pi, right? So the 2 pi's cancel in the omega and the k, and so you can also write this as omega over k. All right, so let's look again at some graphs and how they're related to the equation of the sinusoidal traveling wave. Here we have a history graph at x1. Here we have a snapshot graph at t1. Notice that it's sinusoidal whether I graph it in terms of t or graph it in terms of x. Why is that? Well, if you look at the equation for the d as a function of x and t, notice that it's sinusoidal in both variables. If we're doing a history graph, then x is a constant. We're just fixing x, so kx1 is a constant, just like phi1. And all you get is sine of constant minus omega t. So that's a sine function, so it looks like a sine. If you fix t, on the other hand, as say t1, then x is a variable, and omega t1 plus phi naught is a constant. So again, you get a sinusoidal curve. Okay. Wave motion on a string. Notice that the actual motion of each point on the string is up and down. the wave itself goes to the side, but the points on the string go up and down. This is characteristic, as we were just saying, of a transverse wave. That is, the disturbance is perpendicular to the wave motion itself. Whereas what I mean by wave motion is the motion of the wave, okay? So the wave is going in the positive x direction, but the wave particles are going up and down. So we need to distinguish between the v of the wave and the v of each particle on the string, okay? How do I get the v of each particle on the string? Well, the v of each particle on the string is a different number depending on which particle it is we're talking about, as you can see from all these different green arrows. And that's just given by the derivative of the displacement function with respect to time, just like the velocity of anything is given by the derivative of the displacement with respect to time. So that gives you minus omega a times the cosine function, because when you differentiate the sine, you get the cosine. So you can see that the v's are going to be different at every different value of x and at every different value of t. So that's exactly what you'd expect from this picture. The velocity of the wave, on the other hand, is a constant number. This is just one number given by lambda over the period, or by lambda times the frequency, or by omega over k, whichever you like. But this velocity is going to be a whole bunch of different things. It's a whole function. It's not just one number, it's a whole bunch of different numbers. Okay, so here we have a sinusoidal wave traveling along a lightweight string with a wavelength lambda 1 and frequency f1. It reaches a heavier string with slower wave speed and continues on with wavelength lambda 2 and frequency f2. So which is true? Okay, so the frequency has to be the same because that's the energy of the wave. And the wave energy doesn't go anywhere. But the wavelength has to be different because the product of the wavelength with the frequency has to be smaller because it has a slower wave speed. So f1 equals f2, but lambda 2 has to be smaller than lambda 1. Okay? All right. We're going to skip this advanced topic, but if you want to read through this in your chapter, please feel free. This is where the wave equation comes from. He actually derives it with a not too difficult derivation, looking at individual pieces of string and exactly how we get the differential equation for the wave equation on a string. So, as I say, I'm going to skip the derivation, but I do want to talk just a little bit about what the wave equation looks like. This is a very famous equation, the wave equation for a string, and this tells you the dynamics of motion on a string. I'm not going to test you on this, so you certainly don't need to memorize this, but notice that it's a second-order differential equation in both time and space, and that the second derivative with respect to time is proportional to the second derivative with respect to x. And why would you expect that? Well, you'd expect that because if we look at the, if we look at the equation for the displacement on the string, if you take two derivatives of this guy with respect to x, you're going to get a constant times the same thing back again, right? If you take two derivatives of this thing with respect to time, you're going to get a constant times the same thing back again, right? But the constant is going to be related to this constant here, and that's why you get the same thing or proportional to the same thing depending. Okay, so there you are. So two derivatives with respect to time, you get the sine function. Two derivatives with respect to x, you get the sine function. And oh well, here it is right here. So here's the traveling wave solutions. I'd forgotten that they put this in here. So if you take two derivatives with respect to time, you bring out two factors of omega, and the sine becomes the cosine, becomes minus the sine. So you get the same wave function back again. If you take two derivatives with respect to x, you get two factors of k, and with the same sine function back again. And notice that the constant out in front is just the square of the velocity. Okay, so here's an example where you're generating a sinusoidal wave. We can write the displacement equation for the traveling wave in the string, and then plug in numbers to get the particular displacement at a particular x and a particular time. So there's the wave displacement for the string, And all you need to know is what these constants A, K, omega, and phi naught are. All right. So the amplitude is the amplitude of the oscillator generating the wave, and you're told that the maximum displacement is at t equals to 0, so you know what that is in terms of the that gives you the phi naught. Okay. So the frequency has to be the same as the oscillator, the frequency of the source. So that gives you omega. And then finally, we need K, right? But we can get K because we know what the string is. We know the characteristics of the string. And so therefore we know what the speed of the wave is. All right. And that's given by the square root of the tension divided by the mass per unit length. Now, since we know omega, or equivalently F, we therefore can find out what lambda is. And so that gives us everything we want to know. Oh, and then we plug in to get the part B. Okay, let's talk a little bit about sound waves. As I said earlier, sound waves are the most important example in this class anyway of longitudinal waves. And notice that physically speaking, what's going on here is that the air molecules get bunched together and then spread apart and bunched together and then spread apart. And the places where they're spread apart is called rarefaction. And it's kind of the opposite of compression, where they're bunched together. So there you are. All right, and here's a picture of a fetus in a womb, which is very much more detailed than when I was pregnant. Mine just looked like a blur, but whatever. Electromagnetic waves are one of the most important examples of transverse waves, and so we should talk a little bit about that. Electromagnetic waves are essentially light. I mean, well, they are light, okay? And light comes in lots and lots and lots of different possible frequencies, but they all travel through vacuum at one speed, the so-called speed of light, which it's the speed of light, so there you are, which is about 3 times 10 to the 8th meters per second. Okay, here is a picture of the electromagnetic spectrum. Notice that it's a logarithmic scale, so this is equally spaced in terms of the exponents here. So this is 10 to the 6th, 10 to the 8th, 10 to the 10th, and so on. Notice that this tiny little sliver here is the part that normal people call light, and we physicists and engineers call it visible light. And we call it visible light because we can see it. So we therefore call it visible light. But it's a tiny, tiny amount of the electromagnetic spectrum. At higher frequencies than what we call visible, that because we can see, is ultraviolet. It's even more violet than what we can see over here with the violet. Bees can see into the ultraviolet, although we can't. So some of the flowers that we think are white are actually colored to the bees. I have no idea how they see it or what they call it, but whatever. Right. Higher frequencies than that we call X-rays. Right. Lower frequencies than what we can see we call infrared because it's redder than red. Lower frequencies than that we call microwaves. Lower frequencies than that we call radio waves. And this essentially goes on, quote unquote, forever, and this essentially goes on, quote unquote, forever. But there's no theoretical limit to the size of the wavelength or the size of the frequency. Well, that's not quite true. I mean, clearly the wavelength would be limited by, say, the size of the universe, but never mind. Anyway, to a physicist or an engineer, this is all light, okay? And all of it travels at the speed of light in a vacuum. Okay, so here's a simple numerical example to get an idea of how long it takes a signal to travel from Jupiter to the Earth. And they all travel at the speed of light c, we want to know how long it takes to travel 800 million kilometers, and so all we have to do is take the 800 million kilometers and divide by the speed, and that gives you our delta t. Okay, let's talk a little bit about index of refraction. I said that all light traveled at the speed of light in a vacuum, and that's true. And in fact, it all travels at the speed of light in non-vacuum also, but on average, it travels slower in a material. And the reason is, physically, what's happening is that it's getting absorbed and re-emitted and absorbed and re-emitted. So it's as if you were traveling, it's as if, I don't know, it's a basketball or something, and it's being passed from one person to another as it goes from one end of the room to the other end of the room. Even if the basketball is always traveling at the speed of light whenever it's in the air, if you throw it directly to the back end of the room, it's going to get there faster than if you pass it from person to person, right? So that's sort of qualitatively why light on average goes slower when it's in a material medium as opposed to in a vacuum, because it's getting passed from atom to atom or whatever. So what we do is we define something we call the index of refraction, which is the speed of light in a vacuum divided by the average speed of light in the material. And that tells us this ratio then tells us what the average speed of light is in whatever material it is we're interested in. Okay, so in a vacuum, index of refraction is, of course, exactly 1, because that's C over C, right? In air, it's very, very, very close to 1. So we're going to assume this is essentially 1. I don't think there are any problems that I've assigned you where this is any different, where you have to carry that many sig figs. But in water, that's a dense enough material that this is significantly different from 1. In glass, it's the average speed of light is even slower, and in diamond, it's even above 2. Okay, so how does that work? Well, as we were saying earlier, the frequency does not change because the energy of the light wave is still the energy of the light wave. So the wavelength has to change because the speed changes. So that means that the wavelength of light, when it's in a material medium, changes depending on what the index of refraction is. So here you can see that the lambda is actually smaller when it's in a material medium. Why is the lambda smaller? Because the speed has to be smaller and the frequency doesn't change. And the speed is just lambda times the frequency. Okay, so here we have a light wave traveling as a plane wave from air into glass. Okay, so if it's in air, notice that they're rounding off. So the index of refraction in air, they're taking to be exactly 1. But it's very, very close to 1 anyway. In glass, the frequency will be the same, but the wavelength will be smaller. So A is garbage because there the wavelength is larger. B is garbage because there the wavelength is the same. So the correct answer here is C. Okay, here we have a numerical example, light traveling through glass. We want to find out what the average light speed in glass is, and we look up what the index of refraction is. The index of refraction is, they're taking it as 1.5, although it actually varies from different kinds of glass. Different kinds of glass have different ends, but whatever. Anyway, so this gives you the V in glass is just speed of light in vacuum divided by the index of refraction. And so notice it goes from 3 times 10 to the 8 meters per second all the way down to 2 times 10 to the 8th meters per second. And then how many wavelengths of light are inside the slide? Well, the wavelength is given by the wavelength in vacuum divided by the index of refraction. And so that gives you the wavelength. And then that, if you've given the thickness of the glass, you can figure out how many wavelengths that is. Okay. Again, we're not going to be doing this advanced topic, so I'm just going to pass right through section 6. Don't worry, we will not test you on any of this stuff. Okay. All right. Let's talk about the waves in 2 and 3 dimensions. Okay. So in 2 and 3 dimensions, we've got essentially the exact same thing as we did in 1 dimension, except now instead of just the one axis in real space X, we've got X and Y, or maybe even X and Y and Z. Let's first look at 2 dimensions because it's a little easier to draw pictures. And so here we have a circular ripple spreading out on a pond. Okay, so you imagine that you've dropped, I don't know, a little rock in the pond, and the waves go out circularly in all directions like this. So the wave is going outwards like that in the radial direction. Okay, and the wave itself is going up and down. So imagine it's coming out and in, or in the plane of the water or the page here. Okay, so we call these wave fronts. Okay, and the bigger the scale that you look on these, the smaller the curvature here is. So if you're very, very, very far away from the source, small sections of the wave front look like straight lines. So we're going to make that assumption that we're very far away from the source, and we're going to think of our wave fronts as planes. Okay, so that's where we get this idea of the plane wave. Okay, so we need to talk a little bit about phase and phase difference, because that's where we're going to get the phenomenon that we're going to be talking about in the next chapter, namely interference effects. Okay, so what do we mean by phase? Well, that we're going to learn right now in this chapter. Phase is the quantity that's in the argument of the sine or the cosine. Okay, so that's the kx minus omega t plus phi naught. That's the phase of the wave, and that's the you then take the sine of this, and that tells you what the displacement is. The phase difference between any 2 points on this wave, or the same point on any 2 different waves, you can just get that as the difference between the thing in brackets. Okay, so the phase at this point is this phi 1 of kx1 minus omega t plus phi naught, and notice that because this is a snapshot graph, the 2 points that we're comparing here have the same time, but they have different x's. So the t's go away, the phi naughts go away, and it's just kx1 minus kx2. All right, and that will be that. All right, so here we have a spherical wave traveling outward from a point source, and that's right here in the middle, right? And we want to know the phase difference between the 2 points on the wave marked with dots. Notice that this is all one phase. That is, this one circle is all one phase. This, on the other hand, is halfway in between these 2 crests, right? So remember, 2 crests are exactly 2 pi apart. So this is going to be halfway in between that, or pi radians apart. Okay, so here's a numerical example where we can get the phase difference between any 2 points on a sound wave, and it's exactly like what we were just doing on the slide. Okay, the last thing before Doppler is the idea of power and intensity. Okay, so we know that a wave carries energy. So what about the power? Well, the power is the rate at which the wave transfers the energy. Notice that power has to be in joules per second, just as we were talking about earlier in the course. Has to be in joules per second, which is watts. All right, so that's the rate at which the energy is transferred. Okay, so we can also define the power divided by the area, and we call that the intensity of the wave. So this will be in watts per square meter. Okay, so here's a numerical example. We've got a laser beam. It emits 1 milliwatt of light power into a 1 millimeter diameter laser beam. So what's the area here? Well, we take pi r squared for the area, and we divide 1 milliwatt divided by the area of that laser beam. So that's right here. Here's the 1 milliwatt, and then we have pi r squared, and that gives us the power. Okay, what about the intensity of spherical waves? Well, if we radiate out in all directions, okay, and now we're thinking about this spherically as opposed to on the surface of a pond, we're thinking of this as being surrounded by concentric spheres. So the exact same energy gets spread over a sphere, which has a larger and larger radius as it goes outwards. Okay, so what is the surface area of a sphere? Well, as we all know, the surface area of the sphere is 4 pi r squared. So the intensity goes down like the square of the distance. Okay, so that's why sound becomes less loud the farther away you get. Okay, and we have another scale on which to measure the intensity of sound. We call them decibels. This is on a log scale, but it's log to the base 10. So we have to be careful about that. This is not the natural log. This is log to the base 10. But this is the standard means of measurement of intensity of sound. And there's a graph, excuse me, a table here, which is in your book, page 445, which gives you an idea of what these decibel levels are in terms of things that you're physically familiar with. Here, the threshold of hearing, you can, I don't know, person sleeping 3 meters away from you, whatever, okay. This is threshold of pain, 130 decibels. Loud as football. Oh my goodness. Whatever. Okay. So so here we have one solo flute, which is 70 decibels. And suppose we have 10 flutists standing close together, so the sound level, oh, sorry about that. So the sound level will go up to 80. Okay, and then here's another numerical example with the blender noise. All right, finally, let's talk about the Doppler effect, okay? Because you can't take an elementary course in physics without doing Doppler, so here it is. All right, so remember that if you've got a source of waves, if it's the waves will be a function of both space and time. Now, if the source of the wave is stationary and you are also stationary, then the wave is going to go in a particular direction and it's going to go away from Pablo and towards Nancy. But suppose that Nancy is moving, or you're moving, or the source is moving. Well, in that case, the speed that it's going to be moving, depending on the properties of the medium, is going to be different, and the frequency is going to be different. Okay, so here's a lovely picture that shows this. Suppose that suppose that here's the source at t equals to 0, but that the source is actually moving from here to here to here to here. Well, in that case, here's the wave that it emitted at t equals to 0, and it's been 2 more seconds or 3 more seconds since then. So then it was here and it emitted this, and then it was here and it emitted this. Notice that Nancy sees the wave crests more frequently than Pablo does. That's because the wave source is moving towards Nancy, okay? And moving away from Pablo. Okay, so that's summarized here on this slide. As the wave source approaches Nancy, she detects a frequency which is higher than the natural frequency of the source, and Pablo detects a frequency which is lower than the frequency of the source. Okay, and here are the equations that express this. Again, you do not need to memorize these. You can look these up, or on tests, I will give them to you, whatever. So here are the equations for an approaching source, for a receding source, or for when you're approaching or you're receding from the source. Okay, and we use the Doppler effect to do all kinds of things. I mean, it's not just for the cops to see whether or not you're speeding, and we'll talk about that in, I guess, another slide or two. But also for weather maps and all kinds of cool things. Okay, so here's a siren emitting a sound wave with a frequency f0, and here we're wondering what the physical explanation is of hearing if this is what it's emitting, why do we first hear a lower frequency and then hear a higher frequency? Well, remember that if you and the source are approaching each other, you hear a higher frequency. If you are moving away from each other, you hear a, oh, crap. Anyway, well, what I was trying to explain was that if the Doppler shift is to a lower frequency, that means it's moving away, right? But if it's a higher frequency, that means it's moving towards you. Okay. All right. So here's a police siren, and we've all heard this. We're stopped at the side of the road, and a police car goes by with its siren, or an ambulance goes by with its siren. And when it's coming towards us, we hear a higher frequency. When it's going away from us, we hear a lower frequency. All right. So there are the equations and right. Okay. Finally, the last thing we're going to be talking about is how we do the Doppler shift for light waves. Now, notice in these earlier equations, we had the velocity of the source or of the observer compared to the velocity in a medium. Okay, that is going to be different here, where we're talking about when we're talking about light, because the velocity of the medium, there is no medium with light in a vacuum. However, we do compare the velocity of the source to the speed of light in a vacuum. So here, this is how we know that, for example, different stars are moving away from us or towards us, is if their characteristic spectra are either blue shifted or red shifted. If the light is going away from us, then it's red shifted. If it's coming towards us, then it's blue shifted. Okay, so we can actually measure the velocity of a galaxy relative to us by looking at how the characteristic spectrum is blue shifted or red shifted. And so here's the equations for that. And that's it. All right, so that's the last subject in this chapter. And in the next class, we're going to be doing some problems from chapter 16.